Okay, so let us start. Yeah, I think. Good evening, everyone. So this is Abhimanyu. I will be taking this interactive session for week 5. Uh, Let us first go over through the content. So I will be going through the bisection method, fixed point iteration, then Newton-Raphson methods for single variable as well as multivariable, and then we will look at the inbuilt MATLAB functions f0 and fsolve. I hope I am audible. Srinit, what's the name? Srinitya, I hope I'm audible. Okay. Yeah, so let us first look at the bisection method. So we'll be looking at this example, uh, which is similar to what sir has shown in the recorded lectures. So the example is 2 minus x plus log x. First, let us go through the theorem which we used for the bisection method. So this theorem is simple that if we take 2 points across the curve xl and xu, and we evaluate the function at those 2 points, and if we take the multiplication of those two function values, if their multiplication is negative, that means there is a root of that function between those 2 points xl and xu, which is because suppose I take these 2 points, xu and xu and xl. Now if I evaluate these functions at these points, so I have two function evaluations, fl and fu. Since there is a root between these 2 points, that means the function value crosses 0 between these 2 points. So if I take the multiplication of fl, fxl, and fxu, then then one is positive and the other one is negative. So the product of those two numbers would be a negative number. On the other side, like if I take 2 points which are on the same side, suppose I take one xu over here and xl over here, and if I evaluate the function at these 2 points, then since both function evaluations are on the same side of the x-axis, in this case above the x-axis, that means both fxl and fxu are positive in this case, and the multiplication is positive. Similarly, if we take both the points at the lower side of the x-axis, then that means we get two function values where both fxl and fxlu both are negative. So their product is a positive number, right? So that means we don't have a zero between those two xl and xu values. So we use the similar method, like we use the same principle. We take two initial conditions which are far apart, such that even though these two values are initial guesses only, we assume that the two values are on the other side of the root. So if the values are on the same side, then the function or the code that we write, it should give us an error that both the values are on the same side of the x-axis. So you should take another guess. Okay. Then we take two guesses, xl and xu, and we evaluate our function at those 2 points. Then we uh, then we check for the multiplication of those 2 points. If it's negative, then that means we have a root between those 2 points, and we take a average of these two xl and xu values to get a new x value. which in this case, if I take the average of these XL and XU values, I should get a value which is somewhat around here. Then we evaluate the function at this value, and we again look for this multiplication of FXL and FXU. Let's suppose this is our new. Suppose this is my X new value. This is my old. This is my lower value, and this is my upper value. So now I will evaluate my fx n, and I will check with the multiplication with fl and fu. So in this case, my fn is on the positive end. So my fl multiplied by fn would be a positive number. That means there is no root between this xl and this xn value. On the other hand, if I take a multiplication of fn and fu, then these two are on the opposite ends of xn of the root x root value. That means there is a root between these two values. So I will replace my lower x value with this new n value, and I will repeat the iterative process. So this is what it's written over here. So we choose two values xl and xu as the two guesses for the root, such that the product is less than 0. And then we estimate the new root as the midpoint between xl and xu. Then we replace xl and xu or xu based on the sign of fx. So what I told just now, if the product is negative, then we replace the lower end of that, and then we repeat the process. So let us look at an example for this. So if I go to MATLAB, so I have written, so we have taken an initial case of, first let us plot the function. So I will just use some random values. Okay, so this is the fx, this is the plot of 2 minus x plus log x, and let us also plot the, so we can see we have two roots over here. One is one root is close to x is equal to 0.1, okay, yeah, 0.15, and the other root is somewhat around 3.14, 3.15. Okay, so now for the first case, our initial guess is 0.1. So which means our initial guess is somewhere around here. Yeah, so this is the point for our initial guess. and the other initial guess is 1. So we will be taking these two values. So we can see that at one side we have a negative fx value, and on the other side we have a positive fx value. So this satisfies the condition, and the midpoint of these two values would be 0.55. So we will come somewhat something around here. And then based on our condition, we would replace this 0.99 or 1 value with 0.55, as these values are on the same side of the root. Okay, so let's first run this section. So I have assumed 0.1 as my lowest value, 1 as my upper value of x. I'm evaluating fx at the 2 points, so I will be getting fl and fu. Then I just need to check if the signs of both those two values, those two initial conditions, is opposite or not. If the if both of these product is greater than 0, that means they are on the same side. So I will just throw out an error that initial guess should have different signs. I will be running the loop for 50 iterations. Let us first, yeah, so I will just run the loop. So I will run the loop for 50 iterations. I'm calculating my new point, new x value as the midpoint of the lower and upper value, and I'm evaluating my function at that new x value. Then this is just if else condition to check whether the new function value is on which side of the root, either it's towards the left or towards the right. So if both the values, the new value and the old lower FL value are on the same side, that means I need to replace that. So in this case, so the first condition means that if my FL value, which is like for our case 0.1, so if 0. FL and F new are on the same side, that means they will be positive. So I need to replace my FL with the new XL values, as these two points are on the same side. The other point, the upper point, is on the other side itself. So we need not to change that. Similarly, if this condition is not true, then automatically we will update the upper X value. Okay, so I will run this part, and if I see my X new value, which is 0.1586. So if I check my function over here, so I should be closer to 0.156 only. I will plot this on the graph itself. So that is my one root for this. Uh, so this is my one root for this problem. Similarly, if I choose another initial condition which is closer to this root, then I should be converging to that root. So to the second root. So if I take so one of the initial guess is 0.1, and the other should be on the other side of this root. So I will take something like 3, something like 4. Okay. So I will replace this with 4. Sorry, I will replace the lower value with 1, upper value with 4, and I will repeat the same process. So this time my function converges to 3.1462. So my function converges to 3.1462, which I think is closer here if we plot this point also. Yeah. So this is the second root. Likewise, if I take both the initial conditions which are on the same side of the root, so instead of 4, if I take 3, then I should be getting an error because both F1 and F3 are on the same side, and FL, FB. So both FL, FB would be or would be 0 for that, would be greater than 0 for that case. So I should get an error. So if I run this entire thing, so I will get an error. Initial guesses should have different signs. Okay. So anyone has any problem in this? Any doubts? Fine, then we will go to the next part. Yeah, so we will look at the MATLAB function F0. So we will try to solve the same problem. So using F0. So the inbuilt MATLAB function, we will be seeing two MATLAB functions, F0 and Fsolve. So F0 and Fsolve both do the same thing, but F0 is only used for a equation which is in single variable, whereas Fsolve can be used for multiple variables. And Fsolve is something like Fsolve internally it uses a Newton-Raphson code, whereas F0 internally uses a code which is similar to the bisection method. So in this also we give a vector of initial guesses with two values xl and xh, which is like lower and upper lower x value and a higher x value. Whereas in Fsolve we only give a single initial guess, similar to a Newton-Raphson method. So if I clear this, yeah. So first let us look at F0, help of F0. Yeah. Uh, So F0 tries to find a zero of a function near x0 if x0 is a scalar, right? Uh, in this case, x0 is a vector of length 2, assumes x0 is a finite interval where sign of function x0 differs from the sign of function x20. So this condition is similar to something to bisection method. In this case, if we only give a single value of x0, then it first finds an interval containing x0 where the function values of the interval endpoints differ in sign, then searches that interval for a zero. So it will automatically try to find a range between the initial x0 that you are given, and it will try to find another x0 where the function changes its sign, and then between those two ranges, between the one x0 value and the other which it found, it will try to find the root of the function. So we can see all the different settings for F0 over here. On the output side, we can also get these three results. So if I only write F0 without any output, without storing any output, then I will only get the X value out of it. That is the solution value. But if I use this syntax with the three outputs, then the first one would be the X value. Sorry, I don't have two screens today, so I need to go to Meet every time. Yeah, so if I use this command, this syntax, then the first one would be the solution for the f0. The second would be the function value at that x, and the last one would be the exit flag. So we have 6 different exit flags. If exit flag is equal to 1, that means we have found a solution. And the other other exit flags means the problem is not being solved. So we need to check the exit flags to see what sort of values we are getting. Okay, that is why you should always check the exit flag whenever you are solving a function. Sometimes the function gives us some value, especially in the case of fsolve, because sometimes the function has exited, indicating that the value of x is closer to 0, but still the f function value is indicating that the value of x, the change in x has reached a certain given tolerance which you have defined. But if we check the function value at those values, then it has not reached 0 yet. So we still have some residue. That means the problem has not been solved completely. But because we have given a lower tolerance value, so the f solve or f0 has exited the loop because they think the problem has been solved. Okay. Yeah, so let us now look at the example. So instead of it, I will just try to do it over here. So there are two methods to solve this. One, I create a function. I will just create. I have just created a function function for f0, which takes as input x value, and I am just outputting the fx value for the given input x. Okay. So if I use something like this, then I just need to write a syntax f, and then f val. Then I will check the exit flag also, and so I need to pass a function handle to this, and the initial values. So I will be outputting 1 and 4 for first case. So I'm getting the output 3.1462, which is similar to what we were getting in the last case, 3.1462. And my function value is 0 and my exit flag is 1. That means the function has been solved. Now if I give the same values, then the inbuilt function also gives an error. Function values at the interval endpoints must differ in sign. Okay. If I only give one interval, then it will try to find the other end of the interval by itself, and which in this case it has taken the which in this case is it has found in this direction. So I am getting the output of 0.1586. If I take run this again, so every time it will be going to that direction. If I take a value which is closer to this endpoint, then yeah, so this time I've taken a single interval which is closer to the second root. So I'm converging to the second root 3.1462. Okay. So this is one way. In this case, we are trying to input the function handle, but we have created a file for the function. The other thing that we can do is just clear this. The other thing that we can do is to create a function handle itself. We'll just create a function handle. 2 minus x plus log of x. So this is my function handle. In this case, I need not to make a function, and I can simply run F0 on this part. So here I will just write func, yeah, and it will give me the same answer. But in this case, I have not created any file and I have not saved the function anywhere. I just created a function handle and I'm evaluating it using the simple F0 command. Okay. So any doubt anyone in this? Okay. Then we will go to the next part, fixed point iteration. So what we do in fixed point iteration is we try to, in this case, suppose we had a function 2 minus x plus ln x. So we just try to, this is our fx. We try to change this function into a format such that we get a function we get a function gx minus x is equal to fx. Okay. So in this case, we will just take this x over here and then we will get gx is equal to 2 plus ln x. And if we convert this, if we open this logarithm, natural logarithm, then we will get a second representation with x is equal to e to the power x minus 2. So we get these two representations. Then we take an initial guess and we evaluate the value of gx at that initial guess, and we store that value in x, in x itself, and then we repeat this process until the x value converge. Okay. So in this case, we will initialize our x with some value, maybe like let's say 1. So we will evaluate this 2 plus log 1, and then we will store this in x. Whatever the x value that we get, we will again use that new x value to evaluate this gx again. So yes, in this case, this is our gx. Okay. And this x is equal to x minus gx is our fx. And in this case, this exponential of x minus 2 is our gx. So we will initialize with some certain x value. We will evaluate gx. We will store the evaluated gx in x, and then we will repeat the process again. Okay. Yeah. So let us look at that example. First, let us just expand this. Yeah, so we will look for two cases of gx. First is 2 plus ln x, and the second one is exponential of x minus 2. So in first case, we will evaluate gx is equal to 2 plus log x, and in the second case, we will evaluate exponential of x minus 2. Okay, so let us look at this. So I am just initializing it to 0.3. I'm taking maximum iterations, 30 number of iterations, and I'm just storing, I'm just initializing my x2, x0, and then I'm repeating this entire part. So this is my gx. I'm storing it in x. I'm calculating my error, and then I'm storing the current x value in x world, and the entire process repeats again. So I will run this first part. Uh, okay, yeah. So x world is not defined. Fine. Okay, I need to do the same thing over here. Okay, so it ran for 30 number of iterations. You can see that my error at the end of this is okay, I will, yeah. So at the end of my at the end of 30 iterations, my error is 10 is in the order of 10 to the power minus 14. That means the change in x is close to 0. And if I check my x value, so this is 3.1462, which is the second root of this problem, right? Now, if I try to change, okay, first let me put a condition on this. So if so if my error goes less than 10 to the power minus 8, then I will just break out of this loop. I will stop the iterations. I will run this again. Let me also store the value of error. You can plot how fast the error converges. Mhm. Okay. Yeah. So now you can see after 20 iteration, my system or my function has converged. My error value, if I plot, so this is the initial error value. Uh, then my error increases, then it starts to, then it decreases continuously, and after 20 iterations, it becomes less than the tolerance that we have given, that is 10 to the power minus 8. Okay, so this is for the initial condition 0.3. If I take some initial condition which is 4, so still it has converged to 3.1462, this time in 17 iterations. If I take something as 0. So our second root, our first root value is 0.15 over here, 0.158. So even if I take something like 0.1, so I am taking a value which is to the left side of this root, and I will run these iterations again. Uh, Still, it has converged to 3.1462, but we have a imaginary part over here, right? Uh, why that imaginary part is coming is because we have a log over here, right? So if I do log of 0.1, so I get a negative value. then this becomes negative. So the next value of x becomes negative, right? So for this, if I evaluate this function for x0, so I will be getting 2 plus log of x0. This is a negative value, right? So for the first iteration, it is fine. My new x value is a negative value. My error could still be some positive number. I'm storing my x old in x. So this error is still greater than 0.1 10 to the power minus 8. So the loop will run, right? But when I go to my second iteration, so now my x value is negative. So if I evaluate my log, if I evaluate this function again, so this is my current x value, the answer value, right? I evaluate this again, so I am starting to get a negative. I am starting to get a complex number because log of negative is it's basically not defined, right? So I'm just getting some number. I don't know what, right? This is the issue with this is the issue with this problem statement with this function, and this is the issue with fixed point iteration also. So we also need to check the values of x that we are inputting into the function is the inbuilt nonlinear functions embedded into our function. Are those inbuilt functions defined for those negative values or not? Like in this case, we have a nonlinear log of x inbuilt into a gx. So we need to check for, like, after every iteration, whatever new x we are getting, is this gx defined for that x or not? If the gx is not defined, then we need to output an error that the the function gx is not defined for the current x, and uh, the program will give error, right? So we can see, like, whatever value we choose, the function will keep converging to the. So whatever value I give for this x0, the function will keep keep converging to the other root 3.1462, right? Yeah, it will keep converging to the other root. On the other hand, if I take the other function, other gx, so we have gotten two gx from this, right? One is 2 plus ln x, and other one is exponential of x minus 2. So if I take the next gx, that is x minus 2, and if I try to evaluate the this function, so if I evaluate it with 0.5 initial condition, just let me clear the function space. Yeah, so I will give the similar check values over here so that we can stop and our tolerances are met. Yeah. So our iterations have converged in 11. The function converges in 11 iterations. The final x value is 0.1586. So in this case, for whatever value of x I give, yeah. So if I go to the other side, then So whatever value of x I give, the function converges to the first value, the first root, 0.1586, right? But yeah, so whatever value of x I give, but the value of x should be less than this root 3.146. I converge to this value of um, I convert to this value of root, right? For this exponential of x minus 2 function, gx value. If I give a value which is greater than 3.146, like something like 3.2, then the program or the function, the iterations diverge. So it goes to infinity. Why is that happening is because uh, if I'm giving some value which is like, okay, let me take x0 as 3.14. Check first. Yeah. So if I give my x value 3.14, I try to evaluate x0 minus 2. So this is 3.1268. Okay, let us first. So this is the plot of x e to the power x. Now if I take some value of 3, like my x1, my x0 is 3.14, and if I evaluate x0 minus 2, then I get a value of 1.14. Now exp of this is 3.1268. So this 3.1268 is less than 3.14, right? So this x minus 2, the power of exponent, the power of uh, exponent, it is decreasing, right? So if I instead let us try to store x also. So I will store it in I plus 1. Here I will just use xi minus I plus 1. This should be my I, no, I plus 1. Yeah, clear. Okay. So now if I try to plot x minus 2, so you see my x minus 2 is a decreasing function, right? But if I take some value of x which is greater than my other root, so my other root is 3.14146. So if I take a value 3.15 and now I run this, so let me clear the workspace. Let me first go hold on, and now let me clear the workspace. I will run this again, and if I plot on the same graph, start as a red line. Yeah. Okay. Okay. Instead of all the values, I should have now closed that. Yes. Yeah, yeah, so this is for the first case. So I have in total 18 iterations. Run this again and I will try to plot the first 18 iterations. Yeah, so even for 18 iterations, it is diverging. Let me just put, yeah. So you can see if I go to a value to the right of 3.14, like the second root, then my x minus 2 it starts to diverge, right? It starts to diverge. So I get a value of x which is infinity, right? Okay. So any doubt in this fixed point iteration? I hope this is clear to everyone. So if I go through the site, then I believe sir had given one more example problem. Yeah. So we had one more example in the exercise. Let us try to solve this also. So this is for the first case. If I take my if I take e to the power x divided by 2 to that side, then I get my gx as e to the power x minus 2 divided by 5. That means 0.2 times exponential of x minus 2. The other thing that we can get is if I keep my x to this side only, and if I take a natural log on both the sides, then I should be getting. So let us try to do that case first. First, we will plot this function. So to see how many roots it has. Just plot it 100. My y would be 5 times of x minus exp of x divided by 2 log x. Yeah, so it's a diverging function. I will also plot the x-axis. Sorry, I need to do a hold on. So I have a root almost close to 0 0.2, and I have another root which is closer to 7.1. Yeah, 7.1, 7.2. Okay, copy this. So for the first case, our gx is 0 0.2 exponential of x by 2. So we'll change x over here, 0 0.2. And yeah, okay. And rest of the program remains the same. Okay. So let us 0 point, okay, let us initialize with 0.05 only. So we have a root. Which is close to around 0 0.2. Don't know why the cursor is not showing. Yeah, so the value is close to 0 0.2. So I will just initialize with 0 0.5 only. I will save this. So let us run the first part. Yeah. So even after 9 iterations, it has converged to 0.2237. Okay. Let me plot that. So plot x comma 0 using, yeah. So we got the first root, and the second root is around 7.2 something. So let us initialize this with 7, with 7. Try to see what we are getting. Yeah. So you can see each time I am still converging to the first root. So whatever the value I take, yeah. So if I take a value which is greater than the second root, then my problem diverges. It's similar to the previous case. Okay. Here also, if I take some initial, yeah. Now let us look at the second gx value that we should be getting for this problem, which is a log of 5x, 2 times log of 5x, right? So right, I will change this. Rest of the thing remains the same. I will clear the screen. Yeah, run this section. Uh, So this time, after 17 iterations, I am converging to 7.1. Let me plot that. So I just need to check the end of x. Yeah. So the second root mark for this problem is 7.1543. I plot that. Yeah. So this is 7.1543. Okay. And if I take something like, still if I take something like 8, so that should actually converge, because log of x is not a diverging function. Like, okay. But in this case, if I take a value which is less than 0.1, then I will start getting this complex values, because this log of x becomes negative then. Okay. So any doubt in this fixed point iteration? Then let us go to the next. So Newton-Raphson. Okay. So this is basically Newton-Raphson is basically first order Taylor series expansion of a function, right? So if I look at Taylor series of a function, let me go. Right. So this is my Taylor series about x is equal to a, right? Now if I take my a value to be 0, then this basically becomes my Maclaurin series. Okay. So I am just trying to find the value of x. So I will take this fx minus fa divided by f prime of a plus a, and that will be my x value, right? So this is what Newton-Raphson also gives us. So mm, yeah, so this is basically y is equal to fx plus f prime of x, x minus x1, right? Whatever I am seeing over here. So if I replace my f of x with y, and my fa becomes fx, and this becomes x, this a becomes x, and this a becomes x1, and this also a becomes x1, this becomes x1, and fx becomes y, right? And I ignore the higher order terms. So I get the formula for Newton-Raphson iterations. Okay. What basically is happening is like why we are get why Newton-Raphson works. Because if I look at this point over here, okay, so I have the value of x1, I have the value of fx1 at this point, right? Now f prime of x, this gives me the uh, slope of this function at this point, right? So this gives me the tangent of this function at this point at x is equal to x1. Now where this tangent intersects the x-axis, I get another point, right? So this is my let me take this as x2. Okay. Mm, I need to take. Okay, so if the call ends, then I will just start the meeting again. You all guys can join again. Okay, fine. Yeah. So where were we? Yeah. So I extend this tangent to this point, and then it intersects my x-axis at some point. Okay. If I call that point as x2, then my fx2 at that value would be 0. Okay. Now I need to find this x2. I know that my fx2 would be 0, so I need to find this x2. So I have 2 points. One is this point and another is this point. I can draw a straight line between these 2 points, right? So that would be like my if I take this value as y, then that would be my y minus fx1. So this is like x2 minus y, x2 comma y. So this is my first point, and this is the other point, right? So I write the equation of line between these 2 points. So y minus f of x1 is equal to slope. So my slope is f prime x1, and what's the formula of line? Y1, y2 minus y1 divided by x2 minus x1 is equal to m, right? So this is my m, this is my y2 minus y1, and this is my x1, x2 minus x1. So now I know that my y is 0, okay? So I get the value of, if I put y as 0 over here, so I get this equation, right? Fx minus f prime x1, x2 minus x1. Now I just need to do some operations, and I get my x2 as x1 minus f of x1 divided by f prime x1. Okay, so this is the update rule of Newton-Raphson. Like I replace this x2 with xi plus 1, this one with I, this one with I, this one with I, right? So this is the update rule for single variable. Okay, for multiple variables, this f prime of x1 is replaced with the with the Jacobian of the system of equations. Okay, yeah. So we can see a graphical representation over here, right? So we draw this tangent. It intersects at some point. Corresponding to that x value, we calculate the fx value. So we get this at the second point, x2 fx2. Then we draw a tangent. We get another x3 value, x3 point. Then corresponding to that, we calculate fx3, and the process repeats until we are until the convergence, until it converges, such that like x2, the difference between the xi plus 1 and xi becomes less than our tolerance. Until that point, this iteration converges. Okay. So we will look at the example. So this is clear to everyone, what Newton-Raphson is doing, why we are getting this update rule, and why it is converging. So if any one of you is in machine learning, like if any one of you do machine learning, then this is what happens in machine learning also, the gradient descent. Gradient descent basically does this only, but it's in 3D, in multivariable, right? Uh, so if no one has any doubt, then we can look at an example for Newton-Raphson. Yeah, for a single variable. So this is my function. Okay, we are solving the same problem, the first problem that we were doing. We are doing this problem only. So this is my fx, and if I write f prime of x, then that would be -1 plus 1 upon x. Okay, so that's what I have written. So this is my f of x, 2 minus x plus log x. This is my f prime x, -1 plus 1 upon x. And this is the update rule that we saw here, right? x2 is equal to x1 minus fx prime divided by f prime of x1. So this is the update rule. I'm calculating my error based on the change in the x variable, and then if my error is less than my tolerance, then I will break out of the loop. Now here I can see that I have not initialized my xold variable, so it will throw me an error. So let me just initialize the xold variable. So I will initialize both the value, both x and xold to x naught only. So for the first case, yeah. So this should work. So now I will run this. Yeah. So it has converged in 4 iterations. So let me give a let me give 3.14. Will converge much faster for that. So it converged in 3 iterations only, and it has converged to 3.1462. Okay. Yeah. So the second root of the problem. Let me plot that also. Okay. Yeah. So it has converged to the second root, 3.1462. If I give an initial condition which is closer to the first root, yeah. So in this case, it has converged to the first root. Okay. Mm, yeah. Uh, Furthermore, if like for the same initial conditions, we were seeing that this fixed point iteration, it was converging in more number of iterations compared to Newton-Raphson, right? So if I run this part, okay, let me first plot the error for that only. Need to store x values. Unable to perform different number of elements. So F is okay. Yeah, sorry. This should also be I, and then this will be a single variable, and 1 upon xi. This will be a single variable, single variable, single variable. This should. Let me plot x. Let me plot the log of this. Let me go to some far away. This conversion in 5 iterations only. Mm, Plot of log of error 1, 2. Okay, sorry, I plotted it on the figure one only. Create a new figure, plot it on this. Yeah. So we get a linear line. So what I have plotted is I have plotted the error at I plus one, the error at the ith iteration versus the error at I plus one iteration, I plus one iteration, right? So this is the error, like x is the error at the first iteration, y is the error at the second iteration. Okay. So in this case, y is the x is the iteration at the second iteration, y is at the third iteration, right? If I calculate the slope of this, okay, so we are plotting the log of error at the current time step versus at the previous time step versus the current time step. So we yeah, so we need so the slope of this curve should be the integer 2 or close to a number 2, right? So if we calculate the slope of this, so we have 2 points. So this is like 30 minus 1.5. Okay, 30 minus 1.4 divided by 13 minus, yeah, 30 plus minus 30 plus 1.4 divided by minus 13 minus 3.2 minus 13.7 minus 0.32. So we get a value that is close to 12. Okay. Now the similar case, if for the similar case, if we see the fixed point iteration method, So here also we are storing everything. Okay, let me just do a hold on our figure 3. So I will run clear the variables. I will run this. Okay, so I will be getting, yeah, I will plot the same thing. Okay, with the red dashed line. Okay, let me do for something which runs for, I need like 3. Let me do 2.5. Yeah. Now if I plot the same thing, so this is if I calculate the slope of this, then it's around minus 18 plus 2.3 minus 18.8 plus 2.34 2.34 16.99 minus plus 0.84. Yeah, so we get a number that is close to 1. Okay, that means the error convergence or the rate of error convergence is linear in the case of fixed point iteration, and it's a second it's with a slope of 2, that is it's quadratic in the case of Newton-Raphson. That is why Newton-Raphson method converges faster than the fixed point iteration for the same function, for the same equation, right? Yeah. So this was the Newton-Raphson for the fixed case for the single variable. Now, if we look at the Lorentz system, so we will look at a multivariate example for the same. We will be looking at the Lorentz equations. So this is a 3 degree of freedom, 3-dimensional system, and it was also the first system to be studied for which showed chaos. Okay, so as per the so we have 3 roots, like as told in the recorded lectures. We have 3 roots for this. One is root 3 and 1. The other one is minus root 3 minus root 3 and 1. And the third one is the origin, which is 0 0 0. So 0 0 0 satisfies all the 3 equations, right? So as I told you earlier, instead in the multivariable case, this f prime x, this is replaced with this Jacobian of the system, right? So we all know that Jacobian of the system is like simply we saw this in the last case, right? So if I go to the previous week 4 lectures, it was okay, it's not in there. I thought I showed you guys somewhere. Fine. Yeah, so the Jacobian is in this case it would be like I would take the differentiation of the first equation with respect to the first variable, which in this case is dx. Then again the first equation with respect to the second variable, and similarly the third equation sorry, the first equation with respect to the third variable. And similarly here I would do for del f2 the same thing, and for the last case I will do for del f3 the same thing. So it's a three-dimensional system, so we will get a 3 cross 3 Jacobian. So this will be our f1, this is our f2, and this is our f3. So if I differentiate the first equation with respect to x, so I get a 1. With respect to y, I get a -1. There is no z, so I get a 0. Similarly, similarly, the second equation, I differentiate the second equation with respect to x, so I get a 2 from here and minus z from here, so I get 2 minus z. With respect to y, I get a -1, and with respect to z, I get a minus x. Okay, and third equation, so with respect to x, I get a y, and with respect to y, I get an x, and with respect to z, I get a -3. So this is my Jacobian. Now, this is a 3 cross 3 vector. This is a 3 cross 3 matrix. And this is, so I'm taking a inverse of this. So this inverse should be a 3 cross 3. So this should be a 3 cross 1, right? So we take an initial guess of, so we take a initial guess of x0 as a 3 cross 1 vector. Then, so based on for this 3 cross 1 vector, we get a 3 cross 1 f vector, and this 3 cross 3 Jacobian, we take an inverse, we get this the slope in 3 dimension, like we will be getting a line in 3 dimension, and then this is the current x, like this x0 only if we are taking the first iteration. So we might subtract this, and then we get the value of x for the next iteration. Okay, so this is the Newton-Raphson in higher dimensions or multivariables, in multivariables. Okay, so we will be looking at an example of this. I Okay, I did not have some, right. So fine, I'll just this is just a function. So a Lorentz function, I take as input a vector x, and I calculate my function f and my Jacobian j, and I output these two variables. Okay, uh, I think I don't have a function for it, so I will just write a script. X0 initialize with 1 to 1. Mm. So tall is equal to max iter. Let me just copy this, and I will just change this for the multivariable case. Okay. So I am getting these two values from my function. Lorentz of x, and then so it should be xi, and then my xi plus 1 is xi minus write inverse of j multiplied by, okay. Yeah, furthermore, this should be like it's a 3 cross, it's a column vector, right? So this should be, so I'll just make this also a 6 cross 1 vector because we have not 6 cross 1, 3 cross 1 vector, right? So I want like every variable should have a value less, difference in less than 1e minus 6. Okay. Yeah, this should probably work. Let us save this. Uh, just for the consistency. Let us clear the workspace. Okay. Yeah. So we can see that our x and sorry. Yeah. So we are getting root 3 and 1, which is one of the solution, right? Now if I change the values to minus 1, 1, and I run this again, so this time I'm getting minus 1.73, minus 1.73 and 1. So minus root 3 and 1. Okay. Similarly, the 0, 0, 0 is one solution. So if I write it like something 0 0.5, 0 0.1, 0 0.4, and 0. So now I am getting a value which is close to 0, right? Okay. So this is there. Yeah, so furthermore, let us also look at f solve, right? So we already saw f0. Let us also see f solve. Okay. Uh, so let's clear this. Mm. So if solve attempt to solve equations of the form fx is equal to 0, where f and x may be the vectors or matrices. So this can solve the multivariable problems, right? Uh, so the simplest case is this. We need to provide a function and the initial guess. We can further provide different options such as the tolerances and all those things, what sort of algorithm we are using and things like that. And if we look at the outputs, then we get different outputs like x, the solved value of x, the function value at those points, at this solved x value, and the exit flag. So similar to the other case, we can see different uh, different uh, conditions for different exit flags, right? And we can also check the output number of output iterations it took, and then we can also find out the Jacobian at this solved x value. Okay, so let us first solve the simple 1D problem, a single variable problem using fsolve. So I think we already had some function. Yeah. So we already have this function func for f0. So I will just I will just use some initial guess of suppose 2. Then my x should be solve function handle and the initial condition. Right? So we get the equation solved, and this is our value. If I give multiple outputs, I don't want to see the number of outputs, so I can use a tilde in place of that, and then write the next output. And in this case, let us see iterations and then Jacobian. Okay. So it took 3 iterations. This is the algorithm it is using. I don't know what function count is. You guys can check online. This is the function value at this x value. So we are close to 1 e minus 6. So the by default, this fsolve by default uses a convergence criteria of 10 to the power minus 6. No, I don't. Let us check. There is some option to get this. Okay, we can see the default. Let me just go to Google. Yeah, so the default is 1 e to 1 e minus 6. We can change it based on our requirements. Okay, and the way we do it is we just create a options optimization options, reltol, so I will do 1e minus 10, appstall, 1e minus 10. So this is the relative tolerances between the consecutive iterations, and this is the absolute tolerance, absolute function tolerance, right? This should work. This should optim options absolve. Just like that. Okay, yeah, so we don't have that. I think I got confused with the absolute tolerance and relative tolerance of OD45. Sorry. So we have other options for this, which you can see over here. So we can choose the algorithm, what we want to use. We have the gradients, max change, differential, difference, final difference, minimum change, things like that. We have max number of iterations, and then we have this optimality tolerance that we can edit. So there is no appstall and reltol that is there in the OD45 solver. I got confused with the two. Yeah, okay. So you can see over here, right? So we will just solve this. Yeah, so we get this value of x. Now if I use a different x0, instead of 2 I use 0.5. I run the same thing. Let us not, let us just check these three. Okay. Yeah, so we are getting the first value 0.1586. The function value is close to 0, and we have a flag of like we have flag value 1. That means the function has evaluated correctly and run correctly. Okay. Now for the similar problem, for the same problem, uh, not for the same problem, sorry. Uh, for the multivariable case, we already had a function somewhere. Yeah. So this is the, so we only need to input the function, right? We don't need to input the Jacobian into fsolve. So I'll just use this Lorentz equation function. So it's the same function, but we have just removed the Jacobian part. Okay. Uh, we will use the initial conditions 1, 1, 1, x, f val, flag, Lorentz to x, and I will use this x0. Sorry. So flag is 1, fval is close to 0, and we get this solution root 3, and 1. So we can see that our evaluated function is close to 0. It's 1e minus 9 basically, right? So we just need to create a function handle like this, and we need to run the mhm, we need to just use create the function handle, give the function handle as input to fsolve, and the initial condition, and fsolve takes care of the rest. Okay. So if I change my x0 to -1, okay, let me take -10, -10, and 10. So it still solves the problem, and this time I'm supposed to root 3, root -3, -√3, and 1. Okay. Yeah, so this is from the problem from the last week's lectures. Now let us take a look. Now let us take a look at the sample problems. Yeah. So I will be solving this non-graded assignment. Okay, so we have in total 3 problems. This is like so we already have the code for all these problems. We just need to change the function value in the code, right? So this is for a single variable. So we will change the Newton-Raphson code that we have to accommodate this problem. I've already done that. So this is the same Newton-Raphson single problem. I just changed the FMDF based on the given problem, right? So I just entered this as fx and this as my f prime x. Okay. Uh, so this is the update rule. I'm calculating error and then I'm checking the tolerance. Okay. So they have asked us to, with the initial value of 0.3, run the first iteration and report the value of x1 so obtained. Right. So we need to run this loop one number of times. So let me just change the max iteration to 1. That way we will be running this for only one time. Otherwise, you can use the breakpoint method to do so. Okay. Or else we can just store x values. Like we can change this to xi -1, and then we can store all the x values, and then we can check what value of x we got after every iteration. Okay. I'll just use this. It's the simplest method. Yeah, I need to create x old. Okay, and so I get my x as after one iteration 0.1004. If I just check this one, so I will just check that part. Yeah, so this is correct. Okay. Now also report the approximation error. So we got our error as 0.1996. Hmm? So you can say this is like I just need to subtract 0.1104 with 0.3 and I get this. Also repeat the Newton for the approximate error. Okay, so I just need to run the two number of times and I will get the second part. Yeah, so I'm getting 0.044. I will just write 0.0444. Okay, that's what I'm getting. And now, yeah, so I will just change this to 3 and I will get 0.0265. Okay. Repeat the iterations of Newton-Raphson method until the approximation error falls below. How many iterations does it take for it to converge? So my tolerance is 0.1 minus 5. I will just take this as a large number and we will run this, and the last value of I that we get, that is the number of iterations. Okay. Yeah. So we get 6. So after 6 iterations, we get a value that is less than that. So I will check for this and I'm getting 104. So that means this is correct. Okay. Next is fixed point iteration. So we'll solve the problem one using fixed point with same initial guess as before. Compute the error at each step as well. For this, we need to write the original equation as this. Run the first iteration of fixed point method and report the result. So I have also done this part. So this is the same as the fixed point iteration code. I just changed the this update rule based on the rule given in the function. Okay. So I will just run it for one iteration. The workspace. Just run it for one iteration, and I need to report the result. So I get after one iteration 0.1642. Okay. So this is different than what we are getting using Newton-Raphson, right? We are getting a value which is much smaller. After another iteration, report the result. So this time for two number of iterations, I'm getting 0.1788. And third iteration, so we just run it for three number of iterations. I'm getting 0.1765. I will check this. So 2 by 4, this is correct. Okay. Now the last problem. Let us solve the example from problem 1 using fsolve and f0. Solve the problem using fsolve using same initial guess x0 constant, report the result. Okay. So we need to create a, this is a problem. So either we can create a function or we can, sorry, yeah, or we can create a function handle. So I will just create a function handle, and I will just copy this part, right? So this will be my function handle. Sorry. Yeah. So this will be my function handle, and I can simply pass this to my fsolve. I will use x fl flag. Okay. So we use just these three to get, and they have asked us to first solve using fsolve. Okay. The rate x, function x, and 0.3. Yeah. So exit flag 1, yeah, so it solves the problem and I get 0.1768. So if I run this for long number of time, so I'm getting the same result, 0.1768. Okay. Yeah, so I'm getting 0.1768. Solve the problem, use the initial guess in the range this. Yeah, so you can see that the solution is 0.1768. Okay, let us check if we have some other solution also. If we have no solution, then we can use it, check it using solve only. So instead of 0.35, so I'm still converging to this only. That means there is no solution between these two. So I should get an error, right? So let us just check that. So we already have a function handle. I'll just change this fsolve to f0 and this to a vector. So 0.3 and 0.5. Yeah, so these points must differ. So that means I'm getting an error. So just need to enter 999. This should work. Yeah, so this two is correct. Now the fourth part. solve the following set of equations in two variables. 12 minus y minus 25. If k is equal to 15, initial guess of 2 comma 2. Please solve the above equations using fsolve. Right, so I can create a two-dimensional function handle, or I can just write a function. Okay, let me create a first two-dimensional function handle. Let us see if this works or not. I myself have not created a two-dimensional function handle before. Minus 10, 25 into x into y divided by k plus. So they have given us k value of 50. So I'll just write 50 over here. I will write the second equation. 4 minus 16 to y yeah, so so if I give a value of I should get a 2 cross value. So I think this should work. So please report the final value of x for this problem. Please report the final value of y for this problem using xsolve. So we just need to write. I usually just check the flag value. So we can write a tilde for the values that we don't want, right? Fsolve. I need to input the function handle x comma y, function x comma y, and my initial guess, which is in this case 2 comma 2. Okay, so let us create this like so I solved it using 2 comma 4, right? So I'm getting the same result. Now let me change this. Yeah. So I'm getting a flag 1. That means the problem is solved correctly, and the value of this. So I need to output value of x. So that would be 5.0571, and this should be 3.5714. Yeah. So this is correct. Okay. So we created a function handle like the two function. This function handle is also correct, But the reason it's not working with fsolve is because, yeah, so this basically it means that we have to separate vectors x and y, right? So this is why the fsolve is giving us an error. We just need to like combine all the variables into one. So then we create a function handle like this, the second one. So where you've combined x and y into one, into single x, and then I'm writing x1 and x2 over here. Okay, so this works. Fine. Yeah, so this is, yeah, so this is everything from my side. Mm, I will try to change the I will try to change the meeting link from Meet to either Teams or Zoom, so that we can continue the entire 2 hours from the next time. Sorry for this, but I hope you can go through this recorded lectures, and I will upload the presentation and the codes on the drive link so you can access it from there. Uh, Thank you all. See you next week.